Welcome to the Idiot's Guide to Mass Spectrometry. This is an extra credit video tutorial for Dr. Hardinger's Organic Chemistry 14C lecture at UCLA. In the nature of staying within my 15-minute YouTube time limit to explain mass spec, I've gone ahead and written out all the necessary notes for this video, scanned them and put them into a PDF. If you'd like to download the PDF for your own use or to print it out, you'll find a link to the PDF in the description of the video. So let's get straight into it. Spectroscopy, spectrometry, what are they? What can we learn from them? These definitions are taken directly out of the lecture supplement. Basically, spectroscopy is the study of interaction with electromagnetic radiation with matter. Spectrometry, conversely, is the use of spectroscopy as a quantitative tool. So, practically speaking, spectroscopy would be the act of actually taking a sample substance, an analyte, and running the tests on it, using a spectroscopy machine, whether it's mass spec, IR spec, or NMR. And then spectrometry would be taking that data and using it to make conclusions about the molecule. Mass spec specifically, what can it tell us about a molecule? Well, mass spec excels at giving us the molecular formula of an unknown substance, which we call the analyte. And it could also be used to determine the purity of a substance that we already do know by telling us whether or not there's anything else present in the substance. It determines the molecular formula of an analyte by ionizing it and analyzing its mass using a magnetic field. So, from a principle standpoint, what are we doing when we run mass spec? We're taking a substance and we're placing it in the spectrometer. And what we call the substance the analyte, just for purpose of definition. But essentially what happens to the analyte is it's going to be bombarded with a beam of high-intensity electrons that'll ionize the analyte, turn it into an ion. And that's being demonstrated by this equation here, X being the analyte, E minus electron being representative of the high-intensity beam of electrons. And what this leaves us with is an array of ions. After the whole analyte has been ionized, we have an array of ions that result. And by running all these different ions through a magnetic field of different strengths, basically due to a physics principle that I'm not going to get into, by varying the strength of the magnetic field that we run the ions through, we could determine the masses of all the ions that resulted from ionizing the analyte. And we basically have a readout of the mass of everything that results from ionizing our sample. And this is going to be very useful to us because we could compare the abundances of the ions and basically use them to interpret exactly what the formula of our substance is. Let's get into some of the terminology. Capital letter M, the molecular ion. This is the ion that the spectrometer analyzes. We define M as the molecule, the variant of the molecule we've analyzed that's comprised of the lowest mass atomic isotopes. Since mass spec is so accurate at determining mass, the individual isotopes of the atoms that make up a molecule will come into play when we run mass spec. So let's say we have an alkene like butane. Most of butane is going to be comprised of carbon-12 because the natural abundance of carbon-12 is so much higher than the natural abundance of any other form of carbon. So most butanes we run through the mass spec will have carbon-12. A small amount of them will have a heavier carbon. We're going to be able to identify those because they'll register as having a higher mass. But M is always going to be the molecule with the lowest mass atomic isotopes. M to Z, the mass to charge ratio, gives us exactly, self-explanatory. It gives us the ratio of the mass to the charge of a particular analyte. The charge in the denominator of this equation, for our purposes, is generally going to be 1, which you could see through the equation we have up here. X has become the ion X plus, which has a charge of 1. So hypothetically, if we were given a substance and were asked to calculate the M to Z ratio of M, the molecular ion for that substance, what would we do? This should say calculate the mass to Z ratio of M. There should be an of M right here as written above. But essentially, let's say we're doing this for butane. Well, we have butane 4-carbon alkane. We draw the hydrogens in. We have the formula for butane is C4H10. Since we defined M as the version of butane with the lowest mass isotopes, we take the 4 carbons and we multiply them by the lowest mass isotope for carbon, which is 12 AMU. We do the same thing with hydrogen, and we're given the M to Z ratio for M for butane is going to be 58. Sometimes when we run mass spec, during the ionization process, the molecule that we've put into the machine comes apart. Since we're ionizing the molecule and we're bombarding it with high energy electrons, it's natural and very common, actually it's uncommon that this doesn't happen, that the molecule itself fragments. We can identify fragment ions on a mass spec plot extremely easily. And we could do this because we know that we've already defined capital letter M as the variant of the molecule that has the lowest mass. So if anything comes up on the mass spec plot, which is shown here that's lower than M, we know that it can't be M, we know that it can't be the molecule, because M has the lowest possible mass. So anything to the left of M, anything with an M to Z ratio lower than M, we know must be a fragment ion. You might see these represented in a table as M minus H, M minus 2H, etc. What this means is the mass of M minus the mass of hydrogen, which is 1. So that's fairly self-explanatory. Conversely, since we're dealing with isotopes, they're going to be heavier variants of the analyte. M plus 1, M plus 2, etc. This is, as we saw with butane, some versions of your analyte are going to be comprised of atoms that weigh more than the minimum that they can weigh. What we're going to get in a mass spec plot is a readout of the relative abundances of all the ions, including the fragment ions, to their M to Z ratios, to their masses. So for this particular molecule, which I'm not going to attempt to name on the spot, although if you want some practice with naming, I guess that would be something good to do in your own time. For this particular molecule, we're given the M to Z ratio of M is 452. M is represented here, right? We could identify M if we weren't given the molecule. We would probably be given M on the plot, but if we were given the molecule and we were just given an empty graph and we were asked to say, where is M on this graph? Well, we could find that out by calculating the M to Z ratio of M. We could find that out by looking at the molecule and figuring out what it would weigh with its lowest mass isotopes. And that was the first example that we did earlier with the butane. Some terminology pertaining to the mass spec plot. The base peak, by definition, will always be the highest peak on the graph. Whether it's M, whether it's a fragment ion, as it is in this case. I'm not particularly sure how great the resolution of this will be once it's uploaded, but here it's 257. This is our base peak. For purposes of convenience, mass spec will usually give a readout where the highest abundance will be given 100%, just because everything then is going to be measured relative to that. So the highest peak is always going to be our base peak. M, we've gone through already what M is. M plus 1 will be 1 to the right of M. M plus 2 will be 2 to the right of M. Due to the fact that this is a complex molecule that leads a complex mass spectrum, the X scale here is relatively large, and for that reason it's hard to differentiate M from M plus 1 and M plus 2. But in an example we'd be given in class, this would likely either be blown up or would be augmented with a table that would tell you exactly where M plus 1 and M plus 2 lay on the relative abundance scale. But basically, relative abundances is basically the heart and soul of why we do mass spec. Relative abundances tell us how different parts of the molecule relate to each other, and from that information we can draw conclusions on exactly what the molecule is. So M plus 1, molecular ion with mass 1 higher than M due to a heavier isotope atom. This would be like the difference between butane with a carbon-12 and butane with a carbon-13. Analysis of many mass spectra leads us to form the conclusion that if we look at the relative abundances of the M+1 peak compared to the M peak, we can use that information, we could use the comparison of the relative abundances to determine the amount of carbons in the analyte. For example, if we're given nothing else besides the following pertaining to a mass spectrum, we could still tell how many carbons are in this molecule. If the relative abundance of the M+1 peak is 5.3% compared to the M peak, how many carbons? Well, we said earlier that if we take the relative abundance of the M+1 peak compared to the M peak, which here they're giving us, it's 5.3, and we divide that by 1.1, we can make an approximation on the amount of carbons in the molecule. 5.3 divided by 1.1 is 4.8, which leads us to approximate that there are 5 carbons in this analyte. This yields some general rounding rules. If the remainder is 0.4 or less, we could round down. So if this was 4.2, we'd say there are 4 carbons. If the remainder is 0.7 or more, we round up, as we did here. And if the remainder is between 0.4 and 0.7, our results are inconclusive. So if this were 4.5, then we would know that our molecule either has 4 or 5 carbons. This wouldn't be done at a lost cause necessarily, because let's say we suspect we have a substance that has 3 carbons. Well, if we yield 4.5, we know it has to have either 4 or 5 carbons, and although we don't know which one it has, we know that it can't be the substance we thought it was that has 3 carbons. Moving on to M+2, things get slightly more complicated, but basically doing the same sort of analysis we did with M+1, we could compare the M+2 peak with the M peak, and we'll learn about the presence of 3 different types of atoms, sulfur, chlorine, and bromine in the molecule. The isotopes of these are shown above and their natural abundances. Basically, looking at the M+2 ratio, comparing it with the M ratio, if we have a ratio of 100 to about 4.4, comparing again, this is the M peak with the M+2 peak, which will be 2 over from it on the mass spectrum. That's indicative of the presence of a sulfur molecule, or a sulfur atom rather, in the molecule. Similarly, a ratio of about 3 to 1 yields presence of a chlorine atom, and about 1 to 1 we know that we have a bromine atom. So if we have a mass spectrum that has a 1 to 1 ratio of M to M+2 peaks, it's indicative of a bromine atom. 2 quick rules before I run out of time. The nitrogen rule tells us how many nitrogens are in the molecule. If the M to Z ratio of M is even, there's an even number of nitrogens in the substance that we've been analyzing. There's an even number of nitrogens in the formula. The opposite is true. If the M to Z ratio of M is odd, there's an odd number of nitrogens in the formula. So we'd have 1, 3, 5 nitrogens. If we have an M to Z that's even, we'd have an even number of nitrogens, which could include 0. That's a careful thing to remember. Moving on, hydrogen rule. This is complicated, but I'm sure if you pause it, you could understand it. The wording is always a little bit convoluted. For a molecule with C carbons and N nitrogens, the max number of monovalent atoms, which is hydrogens plus halogens, because they only attach in one spot, that's what makes them monovalent, is equal to 2C plus N plus 2. Double bond equivalency helps us out when we're looking at different possibilities for how the atoms, will come together and attach. Basically, is calculated by the amount of carbons minus H over 2 plus N over 2 plus 1. The double bond equivalency, obviously, is equivalent to the amount of double bonds you have. So in this molecule, we have a dBe of 1, dBe of 2. These each have a dBe of 1. There are no double bonds. dBe of 4, this molecule has 3 double bonds plus 1 additional dBe that we add if we form a ring. So these rings here and this benzene ring. That concludes this video. I suppose if this video is well received, I'd be more than happy to do one for IR spec and NMR and potentially working out a few examples.